All right. So what I was talking about is that I could calculate the de Broglie wavelength of this baseball, given the mass, which is a fourth of a kilogram, velocity of the ball, 30 meters per second. I get 7.5 for its momentum. And when I calculate the de Broglie wavelength, I get a very, very small wavelength. Okay. Which the wavelength of this ball is very, very small. The de Broglie wavelength is, and really the de Broglie wavelength is not really significant until you get into situations or environments where the de Broglie wavelength is commensurate or the pretty much the same size of the dimensions of the environment that it's passing through. Say, if you're passing through a little tube, and the tube has a dimension of 1 times 10 to the negative, or 70 times 10 to the negative 10 meters, which is 70 angstroms. If your de Broglie wavelength is pretty much the size of the holes that you're passing through, then you're going to start having problems. You won't be able to use Newtonian mechanics. You'll start to have to use quantum mechanic descriptions, because your particles are going to no longer behave like particles. They're going to start acting like waves. They're going to start diffracting and showing all these other different characteristics that are not particle-like but more wave-like. Okay, so that's what de Broglie was talking about. So electrons have a de Broglie wavelength of whatever their momentum is. Okay? And in our everyday lives, how are we affected by quantum effects? Well, one way, we all use computers, right? These computers on your desk, right? Dell, okay? There was something called Moore's Law for a while, and what it talked about was the speed of the computer doubles every 18 months. So your computer becomes obsolete every 18 months. So we were traveling on this curve for a while, because computers were getting faster and faster and faster and faster. And how are they making the computers faster? They were making the chips smaller and smaller and smaller and smaller and smaller. That's how, because they were able to put more components on the chip. Smaller circuit components, smaller resistors, smaller transistors, smaller PNP junctions, smaller this and that, MOSFETs, so forth, whatever you have on a chip, okay? And they reached a certain point where you open up your laptop and you see all these little lanes. It looks like a small little city, right? With streets and all this kind of stuff. The circuit board. So you got an electrical component here, and then you got a flat little wire. This is where the electricity travels to the next component. Okay, so I'm just drawing a circuit board here. It got to the point where the lanes that they were drawing on the circuit board were so narrow that they started being about the size of the de Broglie wavelength of the electrons that were passing through. So the electrons started acting more like waves and particles, and they couldn't predict where the electrons were gonna go. They didn't have reliable electronics. Ohm's law broke down. Kirchhoff's law broke down. Still conservation of energy, conservation of charge, but they weren't able to use conventional electronics. So that stopped. The miniaturization of circuits stopped right there, and they just said, well, we just can't do it, and we started falling off this curve. Computers weren't getting faster for a while. So what they said, well, how we get around this? We want to release the Dell, Inspiron 532, and we want it to be faster than the previous computer. What they decided to do was say, okay, we can't make our circuit CPUs smaller. We'll just double up on the CPUs. So we have dual core, quad core, 8 core. And what we'll create software, our operating system will distribute the load. So if you're running Word if you're running Excel, if you're running a game or something like this, it will just distribute the job over more CPUs, and that's how we'll get faster. And so we've been going along that trend for a while. So that's one way quantum mechanics comes into our everyday lives. Okay. In electronics, through electronics, we couldn't make circuits, but only so small because of quantum effects. Now let's get to the Compton effect. The Compton effect kind of underscores the idea of quantization of energy, in a way. It talks about what it really talks about though is the interaction of a photon with an electron. Okay, so you have the Compton effect is, okay, I'm just going to try to describe it in one sentence. You got a photon coming in, it's hitting an electron at rest and scattering at rest. And they scatter. The electron goes away. So your photon is sort of like a cue ball, and your electron is sort of like an 8-ball. Okay, and so the photon scatters somewhere, and then the electron scatters off at an angle. All right, and your photon was initially going in a certain direction, and it scatters at this angle off the original direction of theta. By an angle, it scatters at an angle theta off of its original direction. If it was going straight, hit the electron, it scatters off at that angle. Now, and it loses a little energy. Okay, the energy of the photon. Okay, so if it's coming in at this wavelength lambda, after it scatters, it gives the electron energy. It gives the electron kinetic energy. So we know when a photon loses energy, its wavelength changes, its frequency changes. Okay, how does its frequency change? When it loses energy, its frequency gets lower. When it loses energy, its wavelength gets longer. Okay, so this lambda prime is longer than lambda, so it gets red shifted. So if it's like greenish, it'll turn like little red. Okay, so if it comes in red, it'll probably get shifted infrared. And the electron will have its energy and it will go in this direction. And all of this is described by this equation right here. If you know the wavelength of the photon after the collision, and the wavelength of the minus the wavelength of the photon before the collision, h over the mass of the electron times c equals 1 minus the cosine of this angle theta, where theta is, again, the angle between the original direction of the photon and its scattered angle. That's the Compton effect. Okay? So it just describes the collision between an electron and a photon. The electron is at rest. The photon has a wavelength of lambda, and thus an energy of h c over lambda, or h times the frequency, or a momentum of h over lambda. Either way you want to describe it. You can describe it in terms of its energy, or describe it in terms of its momentum. Okay. So it describes this collision with just really, m is the mass of the electron, c is the speed of light, h is Planck's constant. So these are constants. So this is 9.11 times 10 to the negative 31. This is speed of light. 3 times 10 to the 8. This is 6.63 times 10 to the negative 34. So you just really got 3 parameters here. the wavelength of the light initially, the wavelength of the light after it's scattered, and the angle between those two directions. Okay? And, okay, I believe that's good. Okay, now, so 29.5 talks about the de Broglie wavelength and the wave nature of matter. So we talked about that. We talked about that before here in 29.6. But let's just read this, see what else. What are they adding to this? The de Broglie wavelength of lambda of a particle is given by 29.8. Okay, it's also given by 29.6 if you arrange it, algebraically, where h is Planck's constant and p is momentum of the relativistic momentum of the particle. Is the magnitude of the relativistic momentum of the particle. Okay, because of its wavelength, a particle can exhibit wave-like characteristics. Okay, which we talked about that. The wave associated with the particle is the wave is a wave of probability. Okay, what do they mean by that? That's something that we have not discussed. A wave of probability. Okay, so if you talk about an electron as being a wave, and I want to ask you, okay, so if an electron is a wave, then where is it? Is it here? Is it here? Is it right here? I mean, this wave is all over the place. Well, the way, actually, when particles start acting like waves, we use a term called non-localized. They're not non-localized, meaning not in one place. Okay? So where is it? Tell me where it is. Well, we don't know where it is. We only know where it is probably. It's probably somewhere where the wave is biggest. Okay? Well, where's the wave the biggest? Well, right here. Well, the way that we do this is we have something called a wave function called psi. And it's actually not one single wave of one wavelength, but it's a superposition of waves. Okay? It's actually like the sum of many different sine functions. Okay? I'm just going to put a kx here, where k can vary from 1 to infinity, and then you got a coefficient here that goes along with this. Different k's, different coefficients here. So different amplitudes, many different sine waves, or many different sine and cosine waves of different frequencies and different amplitudes added up together. Okay? And what we do is we take this function and we say, okay, we can tell you where it probably is. If you want us to tell you where it is, tell us. We can tell you where it is between 2 points in space. Okay, if you take this point in space between A and B, if you take your wave function and you square it and you integrated it and you integrate it over that little segment, you will get a probability of your particle being in that section, okay, on this line. So that might be, the probability might be, come out to be, it's 10%, has a 10% chance of being here. And if you take that integral between C and D, it might be a 20% chance of being here. And if you take an interval or a segment that goes all the way from negative infinity to positive infinity, all of those percentages have to add up to 100%, because it's got to be somewhere on this line, if you have an electron there. So that's what they mean by probability. Okay, but you're not going to be responsible for that on the test. That's just a little bit extra. Okay, quantum mechanics. But the reason why I went into it is because, if we're going to talk about an electron and a particle being a wave, you have to talk about the position of that particle. And we don't really know for sure where that particle is. We can only give a probability of it being at a certain place. All right, and the Heisenberg uncertainty principle gives us an indication of how uncertain we are of a particle being in a certain place. Okay? What the Heisenberg uncertainty principle says in a nutshell is that we can only resolve a particle's position and its momentum to a certain extent. It's not because our instruments are faulty or lack precision or something like that. It's just because of the wave nature of matter. It's because we can't. It's just the nature of matter, the nature of particles. So what are we talking about here? Up here we're talking about delta P sub y, delta y is greater than or equal to h, Planck's constant, divided by 4 pi. What does that mean? This is Heisenberg's uncertainty principle. So is this. But this is Heisenberg's uncertainty principle as it relates to momentum, the momentum of a particle, or the uncertainty in the momentum of a particle, and the uncertainty of the position of a particle. And what it's saying is that if I have a particle y, and it could be x, it doesn't matter, okay, I can only resolve its position here to, depending on what I know about its momentum, to a certain extent. The more I know about the particle's momentum, the less I know about its position. Why? Because of this right here. H over 4 pi delta P. This is the uncertainty in the particle's momentum. This is the uncertainty in the particle's position. The more I know about the particle's momentum, the smaller delta P is. Because the particle's momentum is P plus delta P. Plus minus delta P, I guess you could say. So it's the actual momentum of the particle plus minus this uncertainty. Okay? Likewise with the position. It's the position of the particle plus minus the uncertainty. So this is the uncertainty. It's not the actual momentum or the actual velocity. I mean the momentum or the actual position. It's the uncertainty. So the smaller I get this, the closer I get to knowing exactly what P is, the larger my uncertainty in the position is. And likewise, if I trade places with these guys, I put delta y down here, delta P here, multiply by delta P on both sides, divide by the uncertainty and the location on both sides. The more I know about a particle's location, the bigger this gets. The smaller this gets, the bigger this gets. The smaller delta y gets, the larger delta P gets. The more I know about a particle's position, the smaller this guy gets, and the less I know about the particle's momentum. So that's all that's saying. Okay? And that also comes about because of the wave-like nature of particles. And the same goes with energy, the state, the energy of a particle. If I go to measure the energy of a particle, I'm going to be off by delta. I can only resolve its energy exactly to an uncertainty of delta E. That's the particle's energy is E plus minus delta E. Okay. So this is the uncertainty in the particle's energy. I don't know exactly what the particle's energy is. I know this plus or minus. Okay. This is delta E. And likewise with the amount of time that the particle stays, or the atom stays at that energy. I was saying particle. The energy. This is the energy of a system, of an atomic system, and this is the time that it spends at that energy. There's an uncertainty in the amount of time that it stays in that energy, and that's what is described by delta T here. The same relationship applies analogously to the uncertainty in the energy and the certainty of the time. The more I know about how long a particle will remain in a certain energy state, the less I know about the actual energy of that system. The more I know about the energy of the system, the less I know about the particle, the amount of time it will stay at that energy. Okay, so that's Heisenberg's uncertainty principle. And I have 1 minute left, but in class we're going to continue with our review of these last few chapters and work out some problems. So unless you have any questions, I'm going to go ahead and dismiss class. Okay, but that's kind of a review of 27, 28, and 29. All right.